Okay, folks, so in today's video we're going to be looking at methods of proofs, which we're going to start a new topic, and we're going to look at a lot of different types of proving questions. Okay, and the first lesson today is going to be about just getting the idea and the sort of basis down for it. Okay, so start off with a wee quick introduction about how we're going to think about this chapter. Okay, now we have already seen a type of method of proof this year by proof by induction. Okay, so that will come back. We'll have a look at that again, but we're going to look at some other ones as well. Okay, so there are several. Let me try and write that again. That's focus writing. So there are several methods of mathematical proof. Okay, that all depend on a series of logical steps. Okay, all proofs start with an implication or proposition and so it is necessary to establish whether the implication is true or false. Right in there, false. Okay. Now, when you're talking about proofs, we'll talk about it there. It is when you're proving something, you're proving it for all cases. Okay, so it's not just enough to give an example that it works for, like, say x equals 3, for example. Okay, and it would work for that, so therefore it's proven. No. However, when you are, if you think something is false, it's good enough just to give a counter example to it. So, for example, if it didn't work for a value, then you've proven that it's false. It doesn't work all the time. Okay, so that is enough to show there. So, look at a quick couple of examples to sort of show you what we sort of mean here. Okay, so example one. Oh, what on earth happened there? Let's go back to that. There we are. So, what's happening right now? Let's try again. So, example one. If x is greater than 5, then 2x is greater than 10. Okay. Well, do you see that that's that, even though this is a basic thing, right, for our level, right, it's given us an implication, yeah? It's saying that, well, if something is that, then therefore it means the other thing. Yeah, it's implying something else, okay? Now, you can obviously see this is obviously true. Okay, this is obviously true. And can be proved by solving two x is greater than 10. Okay, so if we solve that inequality, divide both sides by 2, we would end up x greater than 5, which is what we were implying. Okay, which is what we started off with. Okay, so that's obviously true. Okay, example 2. Okay, if x squared is 25, then x is 5. Okay, so class, would this be true or false? False. You're right. Good. This one is false. Okay. We're not saying the opposite. We're not saying if x is 5, then x squared is 25, because that would be true. What we're saying is that if x squared equals 25 first was true, then obviously then they're saying x had to be 5 here, and that's obviously not 100% right. So this is false. As x could equal -5. Okay. So we've gave. Sorry, that could be. Okay. So we found a counter example to that statement. Okay. So x could have been -5 there. So do you see what I mean about just we don't have to like do it for all x's. We just found a counter example and then bang, that's just shown as false. Okay. So we're going to talk about implications now. Okay. So now that we've got the sort of idea in our head about what we're trying to do here, let's talk about implications. Okay. So, in fact, yeah. So, implication statement. Implication statements are often called if then. Okay, so if something's true or if something is that, then does that happen? Yeah, does that see what I mean? So there's like a two-step part of the sentence there. Okay, statements but the notation for this is that symbol there. Okay, it's like an arrow, 2 lines. Okay, going to the right. Okay, so basically it just allows us to write things a lot neater. So those two things that we looked at there. Okay, so what those questions would have looked like if I used that symbol instead would have been, so if x is greater than 5, then 2x is greater than 10. Okay, so do you see that this first thing they're giving us, they're asking us, does that imply that that happens? Okay, the second one would have looked like, okay, if x squared is 25, therefore is x 5. Okay, so does that make sense? Yeah, just so we'll use that notation a lot more now going forward. Okay, so we'll look at the converse of an implication now. Okay. Converse of an implication. So if statement 1 implies statement 2, then the converse what did I will do, thanks. Then the converse will be statement 2 implies statement 1. Okay. Does that make sense? So if something implies the other thing, then the converse would be, does statement 2 imply statement 1? Okay, so again, going back to our examples that we looked at, example 3, okay, well, if x greater than 5 implied that 2x was greater than 10, which we know that was true, then the converse of that would be, well, if 2x is greater than 10, does that imply that x is greater than 5? Okay, and that's also true. Okay, if I go to the other one, of course, example 4, so the statement was that if x squared equals 25, therefore does x equal 5? Okay, well, we know that's false, okay, because x could be negative 5. However, the converse, so if I flip these statements round, so if x equals 5, does that mean that x squared would equal 25? Well, at that point, that would be true. Okay? So if I knew that x was 5 to start off with, I could then say that therefore x squared was 25. Okay, so sometimes your converses might make something true as well. Okay, it just means it's a one-way implication, it's not a both-way implication. Okay, the first one would be that there. Okay, so if we have oh my goodness me. So something's happened to our board for 2 seconds. Try again. So if P implies Q and Q implies P, okay, then we can say that they're both equivalent to each other, and you can see that I've got my implication arrows going both ways. Okay, P implies Q, Q would imply P. Okay, does that make sense, folks? Okay, right, we'll leave it as there today.